Started then. So hello again, everyone, and thank you so much for joining me today. I would like to talk to you a little bit about my work at Palomar Observatory and the work on the instrument called WorkPol, which is a spectral polarimeter at the observatory. This is the newest, one of the very new addition to the capability of Palomar to observe the universe. And again, my name is Kaew Tinyanont, and I am a postdoctoral scholar at the University of California, Santa Cruz, where I started this week. And up here, you can see the our logo of WorkPol, what the instrument looks like, and when it's being hoisted up to the prime focus. And I know that there are a lot of words here on the title, and I will try to explain what this instrument does and why it is very exciting. So as a brief outline of this talk, I will go through what is polarization and how do celestial objects that we are interested in can become polarized. I will go over how do we actually measure polarization from these sources using a special instrument called a spectropolarimeter. And then I will go through the conception and the construction and commissioning of WorkPol, which is the newest near-infrared polarimeter at Palomar. So to begin, I will try once again to play this video. This is actually from a press release by Maximilla Blanchard, who is also a postdoc at Caltech, but he is now moving on to become a professor at UC Santa Barbara. But he and his group, he and his team recently released a paper with a press release about a polarimetric observation of a brown dwarf. So in that video, they produce a really nice explanation of the of polarization. So let me play it here now, and please let me know if you cannot hear the audio.
Is this a talkie?
It is supposed to be talking, but if it's not, I can do a voiceover. So the audio doesn't go through.
I think you need to enable the computer audio on the in the upper part of your screen. There's a way to do that.
Let's see.
If you pull down view options at the top of the screen.
View options.
It says enable computer audio.
Yeah, I thought I did that when I share the screen, share computer sound. Yeah, it did say something about like it not having a permission and that I have to restart Zoom, but that's okay. It's better if I explain it anyway. So here. All right, so what the video is saying here is that when light is emitted from any source, what you have is the direction of propagation, and that's where that's essentially the direction where light is traveling. And orthogonal to this direction, as depicted as these waves here, the electric field is oscillating in a plane orthogonal to the direction of propagation, which is coming kind of diagonal here. And this plane can orient at any direction, right? As long as it is orthogonal to the direction of propagation. And usually when a source emits light, say like your light bulb and everything, these light waves, this plane of polarization are randomly oriented. So there's no preferred direction from this emission. But if you compare that to something else that have a different light emitting mechanism, like laser, for example, those light is polarized because there's a preferred plane in the, yes, like this. And then we can have a device called polarizer like this. I will demo it in a little bit. That can allow us to study polarization of light. But I think all that you should take from this video is that there is this property of light called polarization, which is essentially the direction of light oscillation in the physical space. All right, so here. So one of the very major ways for polarization to happen from celestial sources is scattering. And on this slide, I will try to explain why a scattering process can polarize light. So as I mentioned earlier, as I just mentioned, most of the emission processes in astronomy, the emission itself is not polarized, does not emit polarized light. So things like thermal emission, for example, which is ubiquitous in astronomy, does not produce polarized light. However, if this unpolarized emission gets scattered by dust or gas in the interstellar medium or in around the source, this emission can become polarized. So here, what I'm depicting here is the blue blobs, or to say stars, and we are looking at it from the top, and the observers, us, are off to the top of the screen. And now, and in this view, we are just looking down at the system. So one rule to remember is that this plane of polarization can be anything as long as it is orthogonal to the direction of propagation of light. So say if the light is coming at you, the polarization can be in vertical or horizontal directions, but polarization cannot also coming at you, okay? So we start with this photon being emitted from this source, and polarization direction is left, right, and also coming at you and away from you. That's what this circle depicts, is that is coming at you, right? So if this photon travels directly upward and then coming at you, the direction of propagation did not change. So both of the polarization components can stay intact. And that light, that photon that just left the screen, did not get polarized. Now compare this with the photon that experienced scattering on the right. So we start with a different polarization. This is up and down, and then coming at you and away from you. But instead of coming straight at us, this photon propagates here to the left. And then in the atmosphere of the star, it gets scattered by a gas or dust molecule. And then it will now travel towards the observer at the top of the screen. And because of that, it has to lose this polarization component, because again, polarization cannot be along the direction of propagation. So this photon has to lose this polarization component before it can travel at us. And now you can see that the photons that experience scattering gets polarized. The direction of polarization is shown here on the left. Now we shift the view from looking down at the system to looking straight on, face on at the system with photons coming at us. You can see that the direction of polarization permitted to travel at us after scattering is this tangent line to the atmosphere of the source. Now, as you know, for most of the astronomical sources, we never see it resolved like this. We never see, apart from the sun, we never see, or really almost never see, a star resolved into a blob with the atmosphere. So what we usually see is that we have to add these polarization components all up into a point source. And what you can already see here is that if the source is all symmetric to us, all these arrows will add up to 0 and cancel them out completely. Therefore, a detection of net polarization, a polarization that is not 0 coming from an astronomical source, is always a good indication that we are dealing with some sort of asymmetry here. Now, this is very crucial because for polarization, you do not need to have any spatial information. You do not have to spatially resolve the source in order to say something about the geometry of it. And this is a very key power of this method. So this slide, I'm showing you some examples of how polarization can arise. So here on the top panels, I'm showing a scenario where you have banded clouds in things like atmospheres or brown dwarfs atmosphere. And I like you to think about this as like Jupiter. When you look at Jupiter, there are a lot of banded clouds. And what those clouds can do is that they can reduce polarization in different parts of the photosphere of the source, and leaving you with some net polarization because the presence of this banded cloud has broken the symmetry. On the top here, the author of this paper, Stoker, in 2017 showed that if you have a banded clouds like this, you get polarization in the up and down direction at about 0.3%. However, if you switch the clouds and the clear atmosphere, you get an orthogonal polarization at 0.4%. So this is one of the ways that we can use polarization to infer what a source looks like, even though you cannot see this source being resolved. Another example they showed in the paper is when you have a dusty disk around the exoplanet, and this will be a scenario similar to, say, Saturn. What you see here is that polarization from the planet itself is not very strong, but the disk or the ring around the source has very, very strong polarization. And this is because all the photons that gets to us from this ring are all scattered. No, nothing is being emitted from the ring. So all you can see is polarized light. And you can see that when you sum it up, a lot of unpolarized light from the planet still dominate the total intensity. So the total polarization gets down to about 1%. And I want you to keep these figures in mind. About 1%, smaller than 1% level, is the typical polarization we expect from astronomical sources. So wonderful. Now we know how photons from astronomical sources can get polarized. How do we actually measure this? So in a way, everyone probably has already measured polarization, and that happens when you put on sunglasses, especially of polarization sunglasses specifically, of course. And here I'm showing a nice view of a river. This is in Thailand, where I'm from, and this is taken actually from the bridge over River Kaew, and you can see a huge reflection from the sky. So what happens when I put on my sunglasses? Hey, all the scattered light from the sky got canceled out by aligning my axis of my sunglasses to cancel out the polarization from this part of the sky. And this allows us to see through into the scary river with all these plant life. So let me go a little bit more into the sunglasses demo. And if you ever go to a polarization talk with no sunglasses demo, ask for a refund, right? This is the key thing that you get from a polarization talk. So usually in the olden day, like when I was in high school in Thailand, this demo is almost always done using two polarizers on the overhead projector, and that's because the emission from the projector itself is not polarized. So you need another polarizer to make it happen. But these days we all own a good polarized light source, which is essentially any LCD screen is all polarized. And I have with me a photographic polarizer, and let me show you how it can work. So here, I can align my polarizer axis to be aligned with my phone polarization axis. And what happens is that all of the light is coming through, right? But when I turn, less and less of the light will here, let me make this a little bit less bright. Less and less of light will get transmitted, and this is because the axis of the polarization start to cancel each other out. And when I turn it completely, the light from the phone is gone. And by this, by doing this measurement, what I can tell you is that light from my phone is 100% polarized in this direction. If I know the axis of my polarizer, I can also tell you that the polarization from my phone screen is in this direction, right? So this is one way that you can measure polarization. And this would be this is in a more schematic view. If you have light coming from the right of the device here, I call it quote unquote sunglasses, but really this is a polarizer, which means it's an instrument that allows one axis of polarization to come through. So here on the left, I have a mix of light polarized up and down and polarized in an orthogonal direction. And I pass it through a polarizer, and only light in this polarization can continue on. If I turn my polarizer 90 degrees, then a different polarization component gets transmitted. So by doing this experiment, I can tell you that my light on the left is 3/5 polarized in this direction and 2/5 polarized in this direction. So that is one method that you can use to measure polarization of light. Now, the problem here is that, remember from before, the astronomical sources have polarization that is not 30%, not 100% like a phone, but more like 1%. So what happened if you use the sunglasses method is that it works like a sunglasses. It cancels about half of the flux, because about half of the light from our astronomical source has a polarization not permitted by a polarizer. And as we all know in astronomy, we have little light to work with. We don't want to throw anything away, right? So this method has been employed in some instrument, but it is really, really not efficient way to measure polarization in astronomy. So we come to method 2, polarimetric beam splitter. And this is how it works in principle. You have similar light coming in from the left. You pass it through this kind of special device called a polarization beam splitter. And then what happened is that light in one polarization, say up and down polarization, gets refracted to the left or upward here. And then orthogonal polarization get diffracted to a different beam coming out of the instrument. So what happens here is that from one picture of the star, you get instead two pictures coming out of it, one with up and down polarization and one with left and right polarization. So how does this magic work? It's really a property of some materials, which is called birefringence. And all that means is that the index of refraction of this material is different for different polarization. And usually this property arises in materials that have a crystal structure, which means there's a preferred plane of alignment of the molecules in this material. And because of that, light that vibrates in one direction can get through much easier than light that vibrates in a different direction. So what happened here is that light with mixed polarization coming in get diffracted differently and comes out as two different beams. And by arranging this kind of material in a prism structure, like what I showed before, like this thing called Wollaston prism, what happens is that you can split the beam of light out into two different beams based on polarization. And we can even go a step further, and this is the device we actually use in work pole. So we don't want to deal with all this bulky crystal, and I will tell you in a little bit why we don't want to do that. But it turns out there's even the super magic material called liquid crystal polymer, and this is a very similar technology that is used to polarize light in the phone. But in this device that we use in work pole, what happened is that the light from the left coming in, propagating through the liquid crystal polymer, gets split based on polarization into two beams. But because of the repeating pattern of the polymer molecules here, what happened is that the light does not just get split by polarization, it also gets dispersed into spectra. So this device makes it perfect for us to build work pole. And I will talk on this in just a little bit. And the piece of optics itself is called polarization grating, because it works as grating to disperse lights. So I talk about polarization, I talk about how to measure it, but why infrared? One thing I mentioned before is that work pole works in the near infrared part of the electromagnetic radiation. So why do we do infrared observation, right? If you talk to infrared astronomers, we will all tell you that observing in the infrared is a huge pain. The sky is really, really bright. In fact, the light pollution at Palomar does not matter to us at all, because the water molecules in the atmosphere are much, much brighter than San Diego or Los Angeles. And in fact, there are even some discussions of bringing research instruments back to Mount Wilson, because in the near infrared, the problem that Mount Wilson faced, which is light pollution, does not really matter to us. So it's a really difficult observations to make, but we still want to do it, and here's why. So this is the first reason, is because when you try to observe very, very tiny polarization of light coming from a star or planets or what have you, what happens is that when light propagates in our own Milky Way, it faced a lot of dust grains in the Milky Way that turns out can introduce polarization by itself. So if you have a star that is not polarized, but you put it on the other side of the Milky Way, by the time the light gets to us, it can be up to several % polarized. And this is a curve here that I'm showing. ISP stands for interstellar polarization from dust. And this the x-axis is wavelength in micron, and optical is here up to 1 micron. And you can see that the peak of interstellar polarization here happened in the optical, and then it decays quickly into the near infrared. So if instead of observing our source at 0.5 microns, or here is about like green light that we can see by our eye, which has peak polarization from interstellar component, if we instead make our observation in the near infrared, like what Whirlpool operates on, suddenly polarization from these dust grains reduced by 50 to 60%. And if we go to a longer wavelength, this gets even smaller. And the reason of this behavior is because dust is a much better scatterer of light in the optical compared to in the infrared. But this is not the only reason why we want to do infrared observations. It is also the case that some interesting things that we like to observe are only bright in the infrared, so we cannot actually observe them in the optical. And here is one of the things I showed earlier, brown dwarfs. Brown dwarfs are sort of like a failed stars in a way. They're almost like a star, but the mass is not high enough for them to initiate nuclear fusion in the core. And because of that, the surface temperature of these objects are incredibly low, and well, astronomically low, which is still about 1,000 or several thousand Kelvin. But at these temperatures, they do not emit brightly in the optical. And you can see here on the left is a visible image from the digitized sky survey, which is again based on Palomar photographic plates actually. And you can't see anything at this source position. But if you instead look in the near infrared using this sky survey called 2 micron all sky survey, you can see a really bright, unmistakable source here. And this is to demonstrate that for some sources like a brown dwarf, you cannot study them in the visible. There's also, this is a good demonstration of obscuration that can happen in by dust. And I'm sure you all recognize the photograph on the right. Here is the famous Hubble's variable nebula. And this is the first light image from the Hale telescope back when it was commissioned. And you can see this beautiful fan-like dusty nebula coming out from this variable star called Armon. And you can see that in the optical, it's very thick. But if instead you look at the work image on the left here, this is a raw, unreduced work image. You can see Armon here, down here as a point source, but the nebula becomes just a wisp of dust. And this is the power of infrared observations that can go through thick, dense dust. Lastly, for things that I care about, which is exploding stars, the infrared part of the spectrum shown here in orange-ish color is really good to probe the light that comes out of the photosphere of the exploding star, and not from the mess of atomic lines that surround it. So you can see here in the optical on the left, there's a lot of bumps and wiggles in the spectrum of this supernova. But once we get into the infrared, the spectrum becomes much, much smoother. And this allows me to directly measure the shape of the exploding star. And I will come back to this topic at the end. But now let's meet our star for today, the wide field infrared camera, a work instrument. So work is a very simple instrument, in fact, or was before we messed with it. It is a camera, which means it makes a pretty picture from light from the Hale telescope. So the light comes in from the telescope from the left and gets messed up by all these lenses collimated into a parallel beam that passes through a filter wheel that allows us to select what wavelength we want to study. And then this light gets refocused onto a detector. infrared detector here on the right of the screen. And because if you know anything at all about infrared emission, we always hear that infrared is like thermal emission, and that is because anything that is kind of lukewarm, a bit warm, will emit some light in the infrared. And because of this, the whole instrument is wrapped in a cryogenic duer that is cooled by liquid nitrogen. So this is a bulk of coolness here. So work instrument is a prime focus instrument. So it lives up here at the prime focus of the 200-inch telescope. And of course, the greatest perk of getting to work on this prime focus instrument is that you get to go up to the prime focus. So this is me trying my best to look not horrified by the height. And you can see that I'm gripping the railing quite strongly there. All right, so after I got up there, messed with the instrument a little bit, along with my colleagues, of course. I did not do this alone. We turned work into a work pole, and there are a lot of things that have to happen for this to for work instrument to turn into work pole. But the key thing is that we insert a polarization grating, this liquid crystal polymer device I talked about earlier, into the filter wheel of work. And what it does is that it turns a star, which would normally show up as a point on the work detector, into 4 spectra. So half of the device is designed to disperse light in this direction, and another half disperse light in orthogonal direction. And by comparing the brightness in all these different spectral traces, we can measure polarization of the source. So you wonder what the real data look like. So to prepare for this talk, I was actually at, well, remotely, but observing at Palomar the whole night last night. And this was one of the images that I obtained from that observing night. And you can see a bunch of black and white lines going crazy all across the field of view here. So to make it easier to digest, I pick one source and kind of Photoshop out everything else. And you can see the bright, or now not so bright, point source here, which is the star that remain undispersed by the polarization grating. And most of the light from this star get dispersed into 1, 2, 3, and 4 spectral traces. And by comparing the light in these spectral traces, we can come up with a measure for the polarization. So this is how work pole works. And it took us all the way from March of 2017 to March of 2019 to get this measurement working. So I am happy to report that work pole now works really, really, really well. And as you can imagine, a measurement that we are trying to make, which is 1% or less than 1% difference in flux between this light spectrum compared to this light spectrum, is really hard to do. So that's why it has taken us quite a bit of time to get that working. But now we can measure polarization very, very well. The best measurement we have done so far is of a bright standard star, and we can measure its polarization down to 0.03%. So that is quite good for a polarimeter from the ground. So with the instrument working now, what are kind of exciting science that we can do with work pole? So I will give you a quick sampler here, and then I will talk a little bit more about my science case, which is the supernova explosion. But first, I already talked about this a little bit in the beginning. Atmosphere of brown dwarfs and exoplanets can produce all kinds of polarimetric signature. And one of the main science goals that work pole was designed to do was actually to detect these bandings and variability in clouds structure of these substellar objects. So that is one huge science case that WorkPole is going to do. The middle panel here, I am showing this beautiful data. Actually, this is not an artist's conception. This is a data of polarization, of dust polarization in our own Milky Way galaxy, and this is measured by the Planck satellite, which is a cosmic microwave background experiment. And what they were able to do is they were able to measure the direction and the strength of magnetic fields in our own Milky Way by observing the alignment that dust grains do to the magnetic field lines. So they were able to produce this exquisite details map of our own galaxy. And recently, as in 2 nights ago, WorkPole was being used to observe some stars in the plane of the Milky Way. So remember from the earlier, I said that stars are intrinsically not polarized, but when you put them behind the screen of dust in our own galaxy, it can become polarized. So 2 nights ago, another postdoc at Caltech, Gina Panopoulos, used exactly this method to observe 10 different stars in our own galaxy to try to measure the magnetic field line in the Milky Way. And she has 4 more nights, so 40 more stars to complete these measurements. And not so far from home, the last science case I'm showing here on the right is of asteroid composition. So we are working with Joe Misero at JPL to use WorkPole to observe nearby asteroids. And with asteroids, what you can do is that as they travel across the sky, the angle of reflection from the sun, of the sunlight coming from the sun to the asteroid and to us is continuously changing. And by measuring polarization at this different position, you can actually tell what kind of composition these minor solar system objects have. So there are a huge range of science cases that we can do with WorkPole, even though we started designing this instrument to look at atmosphere of brown dwarfs. So in the last part of this talk, I will go quick. I will tell you a little bit about what I actually use WorkPole for my science, and that is the shape of exploding stars. So stars, massive stars that begin their life at more than about eight times the mass of the sun, or 8 solar mass, we know that they explode at the end of their life as a supernova. And supernova, of course, is the bread and butter of Palomar, has been in the past and still continue to be these days. I'm sure a lot of you know about Zwicky Transient Facility, the experiment that is being run right now using the 48-inch Schmidt telescope at Palomar. And in fact, first supernova survey is run back in the 30s by Fritz Zwicky using the 18-inch Schmidt telescope at Palomar. So we have a long history of observing exploding things here at this observatory. But what I'm right here, what I want to discuss is that the intrinsic shape of the exploding star itself. So this is a very interesting property because in all of the numerical simulations of these collapsing stars that end up exploding, we see that the process is very, very turbulent and introduce a lot of asymmetry in the explosion. So back several decades ago, the computing powers that we had did not allow us to incorporate 3-dimensional processes into a simulation of these exploding stars. And back then, people would assume that these explosions are symmetric and would produce a spherical ball of explosion. And they use this assumption, put it into the computer, and only compute one dimension explosion. And the biggest conclusion, and it's kind of a thing that observers like myself used to make fun of theorists, is that according to theorists, stars don't explode and supernovae don't exist, right? Because when you don't have three-dimensional features, when you assume that the explosion is symmetric, what happens is that you cannot reproduce an explosion at all. So in the past, even 10 years, people started to realize that once you incorporate realistic three-dimensional processes into these explosion models, you can make them actually explode. There's still a lot of work to be done in that department, but one thing we can do is to provide actual observational constraint of what the geometry and the shape of the explosion actually look like. And if you remember, one of the biggest points that I try to make for polarimetry is that you can use it to measure the shape of things even when you cannot resolve it. And this is done by looking at the cancellation of polarization vectors in the source. So the best studied supernova in the history of observation is, of course, supernova 1987A. And unfortunately, this supernova happens in the southern hemisphere, so there's no observation from Palomar. But what people were able to do, even back in the 80s with Polymer, is that they were able to infer that the exploding ejecta coming out of the supernova is highly asymmetric, and it has an axis ratio, the length along the short side divided by the length over the long side of about 0.5. And these measurements were done early on back in the 80s and 90s. And then 20 years later, we point the Hubble Space Telescope to this supernova because this supernova happened very nearby, about I believe 100 kiloparsec away from us. So this is in the Large Magellanic Cloud, so it's very nearby. So when you point a Hubble Space Telescope at this source, you can actually image the gut of the star being blown out in this supernova explosion, and you can see the shape of the ejecta match really well with what predicted from polarization measurements. Another thing that polarization measurements can tell you is the direction. You remember what I showed on the phone earlier? You can rotate your polarizer to gauge the direction of polarization. It's the same for this measurement. People were able to say that this oblong shape of ejecta has a long axis pointed 14 degrees away from north on the sky. And sure enough, when we point Hubble at it, it looks exactly like that. Now, 87A is a special case. I show here angular scale on the sky is almost an arcsecond, so this is quite large. But for most supernovae, we cannot have any hope to produce this kind of image. So in 2018, another star blows up nearby, and we were able to use work pole to observe it about half a year after the explosion happens. So this is when the ejecta is revealed, and you can start to make this shape measurement. So I was able to use work pole to make a really good measurements of the shape of this ejecta and also its orientation on the sky. So this work is currently being considered for publication, so I cannot show you all the exact details here. But one key feature that I want to point out is that the size of the ejecta, the scale of it is about 600 AU across, which on the sky at the distance of the supernova, which is about 12 megaparsec away, the length scale is about 50 micro arcsecond. So this is so small that even for the biggest interferometry on operating right now, we cannot resolve it. And this is the power of polarization that we can use to gauge the geometric properties of things that we cannot resolve classically. So before I go to my conclusion, of course, I have to say my acknowledgement and thanks all my wonderful advisors, Dimitri and Mansi, that allowed me to take over workflow and use it to do these supernova measurements. I also have to thank Max Miller-Blancher, and I saw that Ricky Nielsen also called in, and I have to thank him as well for getting workflow started and working now today. So I have to thank Nem Jovanovic at Caltech, who helped us push to the finish line and get workflow working in 2019. And Gautam and Jean at JPL, of course, for the conception of this project along with Dimitri. And of course, as Steve mentioned earlier, I cannot thank all the Palomar staff enough for their help throughout the whole process. And I list here only the telescope operator and assistant astronomer whom I work with most while observing with workflow at night. So thank you so much for your help all these years, and all the results that I show today would not have been possible without you. And I did not get to work with Rick that much, but I also have to thank him because of our interaction when we drove up to Palomar and try to make all these measurements in the prime focus cage. He helped facilitate that measurements and make it happen in a very efficient manner. So with that, my conclusions and some parting thoughts. Polarimetry is, of course, a very powerful, but one thing I didn't mention is that it's really, really underutilized. There are not a lot of polarimeter at major observatories at all, let alone in the infrared. So workflow really, really equips Palomar with a very unique capability of infrared spectral polarimetry. The supernova polarimetry science case that I showed earlier, this was actually the first time we can do in the infrared, which means that the measurement is a lot less contaminated by effect from dust in the line of sight. So this is really enabled by this novel instrumentation at Palomar Observatory. And these are all of the science cases that are possible with workflow that somebody at Caltech or JPL communities are actively using to study, and hopefully we will expand this into other Palomar partner institutions in the near future. So with that, I will be extremely sad to not getting to come to this beautiful, beautiful place very frequently anymore, but hopefully I will keep collaboration with Dimitri, and we'll also for him from time to time. And yes, Palomar really made this grad school journey very memorable and very meaningful for me. I grew up in Thailand liking astronomy from very young age, and I think the first observatory name I know was Palomar. So it has been a great honor to get to work here. And yeah, and with that, I would like to thank you all for your attention and take any questions. Thank you.
Yeah, thank you very much. Thank you. I suspect we've got some questions. I know Scott Dixon, you had some questions. You want to start?
Sure. The questions are on the use the little chat feature on Zoom to do it. And I think anybody can do that. But one question I had was with the polarizer and that filter wheel in your instrument. It seems to disperse the light in two directions, plus and minus from the star. Why does it do that, and how does it do that?
Yes. So let me show you this figure. This is not exactly how it works, but So this polarization grading that we put in here, this is a better image. So if you only have a typical polarization grading and you put it in, it will only produce 2 spectra. It will only disperse the starlight into 2 spectra. But what happened is that we designed it so that 1/2 of the polarization grading disperse light in this direction, and another half of it disperse light in this in the orthogonal direction.
Yeah, okay, so the 2 spectra are the 2 different polarizations of light, but then there are actually 4 spectra, I think, aren't there, in the image?
So
2 of them in the opposite plane.
Correct.
What are those?
Yes, so polarization is kind of a little bit confusing to explain. So I say like vertical and horizontal polarization, right? But in reality, when you want to measure linear polarization, what you want is that you want to measure horizontal, vertical, and you also want to measure 45 degrees and 135 degrees. And the reason is because if, say, you have something that is polarized diagonally like this, when you measure it vertically, you get one number, and when you measure horizontal, you also get the same number, because it's a vector projection into this plane. So to completely measure linear polarization, you need 0, 90 degrees, 45, and 135. And that's why we have 4 spectral traces here.
So there's really 2 polarizers, one for 0,
Yes.
90, and the other is 135, 45?
Yeah, exactly. Yeah.
I see.
And another thing that I did not mention is that the work done in 2019 that allows us to use work pole scientifically was that we installed a half-wave plate in front of the instrument. And this is the device that allows us to rotate the polarization angles around around these 4 traces. So the original design, it was fixed, like 0 here, 90 here, 45 here, 135 down here. But what we did in 2019 is that we add a component that allows us to switch to circle like 0, 45, 135 to 1 trace. Yeah, so that's a capability that we have now.
I had a couple other questions. Maybe somebody else wants to chime in.
Well, George Ellery Hale would have been very proud of this very, very efficient use of the light that was available.
Yes, no photons wasted.
Yes. So I have a sort of personal question to ask you. At the beginning, you were working to get the equipment working, and then you began taking the data for your thesis. And I think you said you started in 2017 and you completed your thesis defense not too long ago. When did you start gathering the actual data that went into your thesis defense?
Yes, so I started grad school back in 2015, and back then work pole was still very much work on like sketch in the paper, and I work on building the simulator for the instrument. So basically fake data and try to see if I can work and get information out from those fake data. And the instrument was commissioned first in March 2017, actually February 2017. And the first 2 years were quite difficult because we did not have this half-wave plate to help us deal with a lot of systematic errors that we have in the instrument, which is always intrinsic to any polarimeter. So actually most of the observations from 2017 to 2019 were not as useful scientifically. So yeah, the bulk of the data that went into my thesis came from after 2019. So it was quite a huge sprint to get everything together and done. But with that said, before 2019, I also worked on a different project with Mansi, and that was different other chapters in my thesis. So it's not everything done in 5 months, as it may seem.
I see that things have not changed much, even after many, many decades, in terms of that sprint to the finish.
Yeah.
Can I ask?
So I have
Ken, was that? Ken, go ahead.
I got the impression from a talk by Doug Leonard a few years ago in the Outreach Center that visible light polarimetry is possible with the Palomar instrumentation, but it's not used a great deal.
Yes. So yes, that is absolutely correct. He is basically the wizard of polarimetry at Caltech when he was here, and he was the last person to use the visible polarimeter on the dual beam spectrograph. That was back in, I think, 2004. And he's also the person who got the same instrument working at Keck. So the low resolution imaging spectrograph at Keck also has a spectral polarimeter, and that was essentially his work getting it working there. But yes, I actually should have thanked him in the acknowledgement too, because he is the person who helped me get work pole data working, and he was very thrilled to see the results from the upgraded work pole after 2019. So a bit of a quick story is that in 2017, there was a huge supernova very nearby, only about 7 megaparsec away, which is really close for us. And we observed it with work pole. That happened like a few months after commissioning, and the data were beautiful. The problem is that because of the lack of the half-wave plate, we were not able to calibrate the data to better than 1% precision. And because of that, after a lot of going back and forth with Doug, we decided to not publish that part of the data. So yeah, but I have been working with him a lot. And yes, Palomar has optical spectropolarimeter. It has not been used since 2004, unfortunately.
Thank you. Doug is really a nice person.
Yes. Oh, and mentioning that is in the talk title, but I failed to mention this, and I'm so sorry. But so in measuring polarimetry of the source, often the biggest source of uncertainty is the polarization that comes from the instrument itself. And actually, the 200-inch telescope is almost, if not the most, the best place to do this measurement. And the reason is because there's only one mirror in the light path. Light comes in and it only reflects once. And this reflection is symmetric, so it does not produce any polarization at all. So if we point work pole at a star that we know is not polarized, and we make the polarization measurement, we get pristine 0. Like, we do not have to correct for any reflection from the primary mirror at all. And this is the case at the Cassegrain focus as well. So the 200-inch is really, really good at measuring polarimetry. And this is not the case for most other modern telescopes that use Nasmyth focus that has a 45-degree mirror in the optical path. Wow. For those telescopes, if you measure an unpolarized star, what you get is 3% polarization, and you have to subtract that. So that's a huge, huge benefit that we gain from performing this experiment at Palomar.
Another question I had was, I kind of missed when you described the instrument. I didn't hear what the spectral range or the passband of the instrument was, and what kind of detector material you use. Or...
Yes, of course. So the detector material is also another fun part because before WorkPol in 2017, the infrared detector in work, which is made from this hybrid material called, let's see if I remember this. It
Mercat
has,
Telluride.
yeah, it's a Mercat Telluride device. Thank you. And originally, from I believe about 2012 through 2017, the detector in work was an engineering grade because the original scientific detector has some major problem, and that detector was not good enough for us to make this measurement. So we have to go on a bit of a treasure hunt to find a detector that is suitable. And these detectors cost a lot. I believe the price tag for a new detector is like several $100,000, and we didn't have that much cash. But fortunately, the OSIRIS instrument at Keck was upgrading the detector, so they were kind enough to give us the old detector that has been in the OSIRIS instrument. So, so that was the detector that we have now. It's a Mercat Tel called Hawaii 2 detector made by Teledyne. And in terms of spectral range, we always use WorkPol in conjunction with the broadband filters. So what you see here is J band, which is about let's see, about 1.1 micron to 1.4 micron in the J band. And instrument can also work in the H band, which is about I believe 1.45, 1.5 to 1.8 microns. And see if I can go to my supernova page here. J band is around like here, and H band is this area here. And you can see these huge wiggles in the spectra. These are the strong water absorption bands in the atmosphere.
So we just had a comet in the sky. Can polarimetry tell us details about the shape of the comet and the structure, the physical mechanical structure of the comet? Is that another use for this technique?
It's amazing that you ask. Actually, I think some of our colleagues try to use WorkPol to look at the comet. I have not talked to them if they were successful, but that is of course a very interesting use of it. I think the biggest science case for comet polarization measurement would be similar to the asteroid science case, which is that you can use it to tell in details what kind of like structural composition you have of the materials on the surface, or I suppose in terms of for a comet in like the nucleus of the comet. And the reason is because different materials have slightly different scattering properties. So when it's reflecting light at different angles, you can expect different different strength of polarization in the process.
Something that you really didn't talk about is in regards to polarization is circular polarization, and most of the instruments that I've heard about just measured the linear polarization. Can you say a little bit about circular polarization, what it means, and how you might measure it, or why you can't measure it?
Yeah, definitely. Thank you for asking, so I can delve more into it. So the video that I was trying to play, if it failed, actually has an animation for circular polarization. And what circular polarization means is that if you track the oscillating electric field, if you have linear polarization, then it will be just one plane of oscillation coming at you, right? So if you have some static plane here, you will see the electric field going up and down on this plane. However, if you have two waves offset by a quarter wave, what happens is that when they interfere, the electric field on the plane will not going up and down, but going in circle. So we call that circular polarization. And for circular polarization, we can have this going clockwise or counterclockwise, and we call them right and left-hand polarization. So that is what circular polarization is. In terms of measurement, actually circular polarization is a more fundamental property of light. And this is because when you think about a photon as a particle, a photon particle does not really have any plane of oscillation, but what it has is angular momentum. And the angular momentum property of photons is a direct equivalent of classical circular polarization. And we can produce circular polarization in some very, very special emission process. And if you're familiar with Zeeman splitting in like solar spectroscopy, then this is what happened is when you have strong magnetic field that split spectral lines into 3 or 5 different spectral lines. The central line is not polarized, but the 2 lines that got split are left and right hand polarized. So that is one case where we can use circular polarization to study astronomical source. In terms of measurement, in fact, let me go where it should. In fact, the polarization grading that we put in to a work pole works on circular polarization. So when I show you this slide, is a bit of a lie, or as we like to call it, simplification. But I have cropped out the figure conveniently here. But what happened is that if you just have a polarization grading, it operates on circular polarization. So this beam is actually right polarization, and the lower beam is left polarization. Now, for us, because of our science cases, we are only interested in linear polarization. We put a quarter wave plate. We just cement it in front of the polarization grating, and that way we convert the linear polarization that we want to study into circular polarization that the grating can operate on. But if you were to design a work pole with which can do both linear and circular polarization, should we have a compelling science case, we can definitely do so by removing that quarter wave plate from the grating.
Very, very good answer. Thank you very much.
Is there anything else? Kaew, we've kept you for a long time. You are welcome to tell us to take that you need to do other things. Let me ask if there are any other questions. If not, we are probably getting on time for adjournment.
I have one question. What is the grating actually made of? Is it a liquid crystal or is it a solid material?
It is a solid material, and the name is kind of a misnomer. That's why unlike the phone screen, which are liquid crystal display, which means that these crystals are still in the liquid form that you can modulate them on. This liquid crystal has been fixed in a polymer, so let's see. Yeah, the crystal structures don't change. Actually now, so this technology is actually being used in telecommunication for a long time, but nobody told the astronomers, so we haven't been using it until about 2014, I believe, or no, a little bit earlier than that, but in the 2010s. I guess some astronomer went to a telecom conference and learned about this like really nice optical material and started to put it into an astronomical instrument. But yes, to answer your question, it is in a solid state and is made of this liquid crystal materials that I wish I know the exact composition, but yeah, it's what it looks like is essentially the piece of future. Another thing that I should have mentioned but didn't get to mention is that WorkPol is the first instrument on a major telescope that has this technology built into it.
Thank you.
And the liquid crystal polymer, is this engineered to pass certain wavelengths, particular wavelengths?
Yes, another great question. So the biggest problem with a grating in general, a typical surface relief grating where you have a piece of material that you draw a bunch of grooves into it to disperse light. The biggest problem we have with those materials is that when you produce grooves onto a surface, you prescribe a wavelength to it, and it only works very well at one wavelength, and then the efficiency drops off very quickly around that wavelength. With liquid crystal polymer, we can actually design it and engineer it so that it works very well over a really wide wavelength range. So this polarization grating that we produce can work in the J band, in the H band, and in the K band equally well, equally efficiently. There's no peak efficiency in these wavelengths, and even better, the peak efficiency of a polarization grating is about 95%, which is much higher than anything you can get with a traditional grating. Yeah. So to add back to the point that of wasting no photons, polarization grating goes even a step further in that.
Well, with that, I think we're getting close to adjournment. Dr. Kaew Tinyanont, thank you very much. It's a wonderful
Whose cat is that?
we have 3 kitties living here with us, so they can get quite vocal.
They have been quite vocal. Thank you much. I will send out URL links to this video later this afternoon. And as a reminder, 2 weeks from now, Donald O'Sullivan will be talking about observing the largest structures in the universe. I thank everybody for coming. With that, I'm going to recess the meeting, and we'll see you all in 2 weeks. Thank you very much.
Thank you.
Thank you.
Yeah.
Thank you.